Welcome to this recorded video that will go over the two activities about making and using your own module and plotting with widgets in the Part C lecture notebook for Module 3. NumPy is necessary to run some of the material in these activities, and we'll go ahead and jump to making and using your own module. So this activity is asking you to use the main Jupyter tab on your browser where you launched this notebook to create a new text file in the same directory as this lecture. So I showed this in the video. Really, it's just in here where you have the files. Oh, and I'm doing stuff where I was grading people from a semester, so let me get rid of that. In here, you're going to want to create a file, and you're wanting to call it mymodule.py. So you want to create this as a new text file. So mymodule.py. So I already have one here, but I'm going to go ahead and delete this. And I'm going to show you how I can create it. So I'm going to actually do this with a launcher here. And then in that launcher, which you normally have, where I want to create a new file, is I'm going to create a new text file right here. So there it is. It's called untitled.txt. Now I said in this instruction to say it should be mymodule.py. So let's go ahead and rename this. So I just right click there. I can right click there, or I can do it over here. Say rename, and I want it to be called mymodule.py, not .text. So as soon as I do that, this is recognized as a Python file, which means as I type, you'll notice some color changes that are very useful for seeing how you're doing everything correctly in Python. I want to copy and paste the myfun1 and myfun2 from the Part A lecture notebook into this file and save that as that mymodule.py. So here's the Part A lecture notebook. I've just clicked over to it. I need to have my function A, myfun1. So here's this one. Let's copy and paste it over now. And notice all the coloring is showing up nice in terms of the formatting and everything because I've already saved this as a .py file. And then similarly, I need to have the myfun2 file. Here's myfun2. So I'm just copying and pasting this over. That is it. This is, you might have made edits to these. That's fine, but that's all I'm asking you to do is create stuff into this file. You might want to edit your doc strings or code comments. That's totally up to you. And you might even want to add more functions in here, but it needs to work. So if you do it, make sure it all works. Now that module is created. And so now I want you to create some more code cells below if necessary and import your module as mymod and execute some of the function calls seen in that Part A lecture notebook involving these functions using mymod.myfun1 and mymod.myfun2 because these are now accessible through this module using the dot convention. So I'm going to import my module, right, as my mod. And so then if you go back and you look at some of the types of functions that we had here, like printing this, let's just go ahead and look at some of these in this notebook. All I need to have is print instead of myfun2, which is not defined here, I have my mod.myfun2. And notice it works. It gives me a 5.0. So everything's working as it should. I'm not going to continue to do more of this. You should just copy and paste several more of these options that we're seeing here. This was from myfun2. You could scroll up and see that it works for myfun1. You just have to remember that you're accessing it now as mymod.myfun1 or myfun2. That's really it. That's that activity. So then let's go down to here. You need to make sure this code cell runs in order to run the code cell that I'm going to be talking about, which is plotting with widgets. I need to make sure everything's imported. So this is doing something fancy, a little bit more fancy, is we create a plot function that allows us some granular control over estimating the derivatives of the function and plotting results. Your job is to add comments to every single line of code to explain what is going on and then interpret the results in the markdown cell that follows. So I'm not really going to do all this. I'm just going to kind of explain what it is rather than write, because you should write your own code comments. Try to follow the convention of 2 spaces before your pound or hash sign and, write your code comment if that's in line. If you're going to have code comments above, you don't have that spacing. You just line them up. So you could say, depends how you want to structure it. What we're doing in this plot derivs, I would also suggest, this is not required, but I would add a add a doc string here. There we go. And, I would suggest put a doc string here about plot derivatives, state what it is and the purpose of this function. That's something that I recommend doing, is putting a doc string. You should always have a practice of adding doc strings in. So, initially what we do is n is a parameter that's passed, and we create a regular uniform spacing of n points from 0.05 to 1, where n is a parameter that's passed to the plot derivatives function. So that creates a number of x values that's used for plotting. Then we compute the forward, backward, and center difference approximations to the derivative of the function f that is passed to the plot derivatives function at each of those x values using an h value that is passed to the plot derivatives, where all the x values are determined by this step. On the first axis that is created in a subplot and an array of this is the first of a 1x2 subplot, we're going to plot the function and set the title of the function. Here's the plotting of the function on that set of axes and from that subplot. And then in the second subplot of the 1x2 array of plots, we are going to plot the different derivative approximations. We label each of those plots according to what type of derivative, whether it's a forward, backward, or center difference approximation. And then we're placing a legend containing these labels on the axis in the upper right corner. You can change this location if you want to play around with it. You could read the documentation for what options you have for this. And of course, we're setting it to a larger font size for readability. So we create a function that in this case is x squared times sine of pi divided by x. And then here I'm plotting the functions, and I got a name error. Oh, plot is not defined because I have not imported matplotlib here. So I need to go do that. Where did I import matplotlib? Certainly it had to have been before I did some plotting. So, here would be a good place to do it. Right? And also I hadn't imported differences yet, so I was going to encounter several problems. So, okay. So now I have that imported. I have the plot command ready to go from matplotlib. So now let's run this. There you go. Here's the plotting. You should add all your comments, and then you should play around with this. One of the things you notice is that if you have a large h value, the n is just saying how many points you graph. So it's a coarse representation of the graph for small values of n. It seems you might think 100 points is a lot of points for plotting, but for a function that has a lot of rapid change, then this is not as many as you might think. So if I go up to 300, let's even go a little, much higher. Let's say 1,000. There you go. Oh, that's as high as we go there. You could even try increasing this to even more, like make it go up to 10,000. There we go. You can definitely see that there's some errors. You can definitely see some non-overlap, some differences between these curves because they're not all overlapping each other. As h becomes much smaller, this is a float log slider. Like if I make it 0.001, you can see that you get a much more accurate estimation of the derivatives. The curves start to agree more, and the errors are pushed more to the left where the oscillations are happening at a much more rapid pace as you approach 0. So smaller values of h will give you better accuracy. Larger values of n will give you more accurate plots, or not necessarily more accurate plots, but smoother looking plots. If I decrease this to, let's say, back to 1,000, it's going to look about the same. That's why I don't really do this beyond 1,000. But if you go to 100, again, you see it's not that the computation of the derivative is less accurate. That's determined by h, but we're not plotting it at as many points, and that creates a rougher looking plot. So n helps smooth out the plot, and h helps get the functions that you're plotting more accurate. So that's about it, and that's what you should write in your markdown cell below involving, what the interpretation of the results are. So you should put that in your own words, and remember to add comments everywhere, and I recommend adding a doc string. So that's it. Thanks for listening.